All right, so we are set. So thank you everyone for joining the STINT workshop once more. We are in the last session of the workshop. So we are session number 4. We're over here already. In this last session, we have quite a nice list of students or PhD students, master students, and so on, that are working on related topics on space terrestrial internet working. And the idea is to give some space also to students to spend up to 10 minutes presenting the topics they're looking on. And in particular, we have a list here that we're going to follow. Again, the principle is that we're recording this material. We're going to be making this available offline. And yes, and that's basically it. So I'm going to first introduce our first speaker. We have Timothy Recker with us here, and Timothy will present his talk, which is Simulator for Performance Optimized DTNs. And the mentor of Timothy is Nadia Cortes, who also presented some interesting talk yesterday. So I will stop my screen share here, Timothy, and I leave the floor to you.
Thanks, Juan. Let me share my screen here.
Power on.
How's this?
Yep, excellent.
Connected.
Okay. My name is Timothy Recker. I'm a senior at UC Berkeley studying electrical engineering and computer science. And this summer I got to work with NASA at the Glenn Research Center to implement a simulator for Glenn's version of DTN, which is called HDTN, a performance optimized implementation of delay tolerant networking. And to start off by contextualizing and motivating some of the work I did, I want to talk about what options exist or existed for testing and analyzing HDTN. In the case of testing modules and functions or their composition into complete nodes running HDTN, we have the usual approaches of unit testing and integrated testing. But when we want to analyze an entire network of nodes running HDTN, things get a little more complicated. And usual approaches have involved doing lab tests or emulation using virtual machines, which can be time consuming to set up and configure. And nodes with, well, tests have been run in the lab with up to 10 nodes, but we'd like to scale these tests further, and the setup issues become even more problematic as we scale. And when we want to run tests over like extended time periods, for example, say over the 24-hour rotation of the Earth, then things, it's kind of a bummer if your tests take 24 hours to run. And so the thought was that a solution to these testing difficulties could involve the implementation of a simulator for HDTN. So enter DTN Sim, which some of you are quite familiar with, I'm sure. DTN Sim is a simulator built on the Omnet++ framework for simulating delay tolerant networking. And it's especially good at simulating the routing aspects of a delay tolerant network, and includes classes for simulating ion, including running real ion flight code. And the thought was, instead of implementing our own simulator from scratch, why don't we do something I'm calling as a joke HDTN Sim, which is really a small extension to DTN Sim. Why don't we take the modular design of DTN Sim, combine it with the message passing architecture of HDTN to create a simulator for HDTN that's accurate, maintainable, flexible, and easy to configure and run. So going into a little more detail about each of these elements, in DTN Sim, I saw two interesting different approaches to the question of simulation. And the first method of simulation is, you want to simulate something, you make a simplified model of your subject that encapsulates its core behavior that you want to study, and you run it. This approach is exemplified in DTN-Sim and the routing CGR model 350, which I haven't included in my diagram here, but it sits under routing deterministic in the class hierarchy. And the other approach is to run a coarse subset of the subject and observe what it does, exemplified in routing CGR ion 350, which is a routing model also included in DTN-Sim. So the idea is here is if you want to know what would ion do, why don't you just run ion and say, hey, ion, what did you do with those bundles? Why would you want to do this instead of doing it in, say, a lab? Just for the benefits of simulation environment described before, running an accelerated time, easy generation and plotting of metrics, controllability of the environment, the ability to stop, start, fast forward the simulation, things like that. And I thought this second method was pretty clever and practical. The one problem for us on HDTN-Sim is that the implementation of routing CGR ion 350 isn't something we could really copy. The way it's done in DTN-Sim is you essentially copy a subset of ion code and compile it into the simulator and run it, and then inspect the outcome. But on the HDTN team, the routing is under pretty active research and development and being updated and changed. And I didn't want to design the simulator in a way that it would require major updates every time HDTN changes. As far as I know, the DTN-Sim simulation of ion code is frozen at an older version of ion, which is no problem if ion is stable enough. But for us at HDTN, we wanted something more maintainable for our development purposes. And thinking about how to solve this implementation issue, I took inspiration from the architecture of HDTN itself. And the main point, this is a simplified diagram of that architecture, which doesn't include what happens with bundles and a lot of other things. But what it does show is how HDTN is designed as a composition of separate modules that communicate over asynchronous message passing using 0 and Q. And the module that's of key interest to us is the router module, which is the authority on what happens to bundles when they're forwarded, when they're stored. And so the thought was, why don't we combine the modular aspect of DTN-Sim with the design of HDTN and create something that's accurate but maintainable. The way this is done is in DTN-Sim, we have a simulated network of simulated nodes. Each of them has a routing model that talks to a real HDTN router. It sends link up and link down messages so that the router can recompute routes when it needs to and synchronize its notion of time with the simulator. And it intercepts the route update messages the router publishes to get the information about what is supposed to happen to bundles and take the corresponding action in the simulated environment. And the results of this have been pretty promising. Yeah, it proves to be able to answer useful performance questions about HDTN. Insofar as performance depends on routing decisions and the network topology and the workload or traffic through the network, we've been able to generate useful performance metrics. I won't claim that it can encapsulate every aspect of performance, but some of them it's quite useful for analyzing. It appears at first glance to scale pretty well to large network simulations. We've been able to run tests on the order of 100 nodes, tens of thousands of contacts, 24 hours of simulated time, and less than a second on my personal laptop. There's a lot more analysis and testing here to be done, but the initial results are promising. And another interesting takeaway is how the non-monolithic modular architecture of HDTN has proven to be pretty useful and flexible in ways that I didn't anticipate, and I'm not even sure if the original designers anticipated. It's been able to allow us to implement the simulator pretty easily, and HDTN-Sim can run without modification different versions of HDTN. I've run it with versions of HDTN using contact graph routing, contact multigraph routing, and it works with them without any update to the simulator. So as long as the core architecture of HDTN remains intact, I expect the simulator to continue working with it. I think I might be running low on time here, so I will maybe skip over this, but these are some network flow diagrams generated from the simulator. They were able to show us some like issues in HDTN performance that weren't observed before, and enable us to make enhancements to HDTN routing that improved delivery rate of bundles, for example. The simulator is publicly available in the official DTN sim repository under a branch called support HDTN, if you want to go look at it or use it. It's under development still. And yeah, stay tuned for future updates. That's all I have to show you today. I want to especially thank Juan and Pablo, among many others who are contributed a lot to DTN Sim, made DTN Sim, and were very helpful to me in extending it for our use case. And thanks for listening.
Excellent, Timothy. Thank you for the nice talk. I suggest everyone to go to the chat stream to answer questions. So post comment to Timothy. Meanwhile, I'll move to the next speaker today, which is so Prash Choksi is going to talk us about investigating neighbor discovery for HDTN, and Prash Choksi is mentored by Rachel Dudukovic and Bob Short. So Prash, yes, the floor is yours.
Can you guys hear me?
Yes, perfect.
Hello, everybody. My name is Prash, and today I'm going to talk about investigating neighbor discovery for HDTN. So what is HDTN? HDTN is Glenn Research Center's implementation of DTN, similar to how JPL has ION and Marshall Space Flight Center has DTN-ME. It's optimized for very fast data transfers between different communication systems. So the goal is to get at least 1 gigabits per second of upload and download speeds. DTN also wants to provide mission scalability and mission interoperability, but there's a shortcoming that's preventing it from having or meeting these objectives. Right now, HDTN is not able to dynamically learn about the existence, availability, and addresses of other DTN participants. A solution does exist for this problem. It's called neighbor discovery. Neighbor discovery is a protocol that dynamically discovers other DTN participants in the network. And the two key features it can provide is that it can facilitate scalability as manual configuration of nodes can be significantly reduced. And it can facilitate interoperability by connecting with other DTN participants that use different communication protocols in a heterogeneous network. So what's the need for neighbor discovery for HDTN? HDTN needs a protocol that can dynamically discover other DTN participants in a constantly changing environment, such as the space. And it should be able to tolerate connection opportunities that are not known prior, and it should be able to also handle things such as connections that may disappear randomly. And it should be able to tolerate things such as that and more. Also, we need HDTN to simultaneously discover other DTN services, such as convergence layer adapters and parameters, routers, or even tunnels. I want to talk about a specific neighbor discovery. So this one is called DTN IP neighbor discovery. This one's an IP-centric neighbor discovery protocol where it uses IP&D beacons to send to advertise presence, and they're going to be small UDP messages which advertise presence, and they're sent to either a broadcast or multicast destination address. So over the summer at Glenn Research Center, I was tasked to learn about an existing IP&D implementation. The one I chose was DTN7RS, which is a Rust implementation of DTN based on RFC 9171, and it supported Bundle Protocol 7. So let's visualize how IPND could work. Let's say we have this scenario. We have two nodes, and let's say node 2 is trying to discover node 1. Let's say that IPND is in effect, and let's see what's going to happen when N2 gets closer to N1. We can see that when N2 gets within range of N1, it automatically discovers N1. Now let's see how the inner workings of IP neighbor discovery work. In this case, let's say we have this network topology where we have 5 nodes, and let's consider, let's take the perspective of node 6. Everything's going to be from the perspective of node 6. On the right-hand side, you could see a terminal which has IP addresses. So this is saying that neighbor discovery is working in the background for node 6, as node 6 IP address is 10.0.0.14, and it's sending it's advertising its presence to the multicast destination address, which is 224.0.0.26. Now it's advertising its presence, but it's not able to discover other DTN participants because it's not within range. But let's see what happens when N6 gets closer to the other nodes. We can see that when N6 gets closer to N5, it picks up N5, as we can see in the terminal, where N5's IP address is 10.0.0.13. And this is going to happen for all of the other nodes. So I'm just going to let the simulation play out. So we can see that node 6 is able to discover node 1, node 2, node 4, and node 5. Now let's see what type of information exchange that's exchanged during the IPND process. And this is also from the perspective of node 6. We can see that node 6 is able to discover node 1, node 2, node 4, and node 5. And we can see that all of their respective IP addresses listed, the connection type, their period, and services such as convergence layer adapters. Also, we can query node 6 to see what their what neighbors it has. So in this case, node 6's neighbors are node 1, node 2, node 4, node 5, as mentioned before. So what are other applications of neighbor discovery? One application is for the lunar surface, where DTN-enabled mobile ad hoc networks can be used and discovered using neighbor discovery. Also, we can use inner CubeSat links, which can be used to advertise services and other neighbors and other important data metrics such as storage availability and link status. So why is HDTN very important why is neighbor discovery very important for HDTN? The key point is that neighbor discovery is needed to enable future dynamic routing capabilities in missions for HDTN. So current missions that are supported by HDTN are the ISS-DTN network, potentially laser communications relay demonstration, LCRD, and future LunaNet. What's going to be the impact of neighbor discovery? It's going to, first of all, facilitate interoperability for future heterogeneous networks. Second of all, it's going to facilitate scalability by enabling DTN node auto configuration for larger networks, which is going to reduce burden on network operators, and it's going to prevent them. It's going to, reduce burden on operators for node configurations and increase efficiency. Also, it's going to enable cognitive networking capabilities in the future. And so what are some other neighbor discovery implementations? One in particular is called named data networking, which is unlike DT and IPND. NDND is data centric instead of IP centric. And applications will name data, and the data names will be used during communication. This means that applications will request desired data by its name instead of IP addresses. So NDND raises an interesting question then. Should DTN communication name data instead of nodes? I want to thank the authors of DTN7RS for providing this great resource. And thank you for listening to my presentation. Any questions?
Excellent. Thank you, Prash. I think there is one question for you in the chat stream. So I suggest you go into there and tackle the question. Meanwhile, we're going to go to pass to the next speaker. So we have Dominic Ta here, who is going to give us a talk about diving into the data plane of DTNs. Dominic's mentors are also Rachel Dudukovic and Stephanie Booth. So yeah, Dominic, please go ahead and start anytime.
Can you hear me?
Yep, thanks.
Okay. Hello, everyone. My name is Dominic, and I'm currently a master's student at the University of Washington. And today I'll be talking about the work I did this past summer on applying software-defined networking techniques and data plane programming techniques to delay-tolerant networks. So the challenge that we were dealing with is scalability in DTN. So we've seen DTN demonstrated to work in the small scale, such as on the ISS. But as a solar system internet gets deployed, the number of nodes in these DTN networks is going to be dramatically increased. And managing these large networks with all of these unreliable links is going to be difficult. So we propose using software-defined networking techniques to delay-tolerant networks. So for those who don't know, software-defined networking is a technique used by network operators to manage and scale their large networks. So on the left-hand side of this diagram, you can see a more traditional approach to networking where each of these stacks of boxes could be represented as a router in a network, and the control plane within the router manages the higher level routing logic, while the data plane focuses on getting packets through the switch. And in software-defined networking, the network operators would extract this control plane and place it into a centralized location so that they can manage routing behavior in a centralized location and control the behavior of all of their network nodes. But there's some complications if we want to apply this to DTN. One complication is that these links between the control plane and the data plane, it assumes that you have a link there. And another big issue is that we need hardware that can understand bundle protocol. So we need a data plane that can understand bundle protocol. So that is the problem we were tackling, which is the data plane. So we decided to use data plane programming to program routers to understand bundle protocol. And if we are successful, well, that means we could have hardware that can natively forward bundle protocol. And we could also potentially process bundle protocol faster than we can do in hardware. And we would also have the ability to control network behavior based on bundle protocol logic at the control plane level. So our approach is to use the P4 data plane programming language. It's open source and pretty popular in the field of data plane programming. And for our specific configuration, we have the Netberg Aurora 710 switch that contains the Intel Tofino networking ASIC that is designed to work with P4. So using the P4 language, we would create a data plane program for the switch using Intel's SDK, and we could program the switch to understand bundle protocol. So in our configuration, we have two DTN nodes. Ada and Rho, both running ion and generating bundles. And our goal is to get this router to not only forward these bundles, but understand what is being passed into it at the bundle layer, which is currently not possible. But we ran into some difficulties that we didn't expect because of how popular P4 is and how many things it's been used for. Specifically, bundle protocol is a pretty complex protocol, but P4 has been designed under the assumption that there would be simple networking protocols like IP and TCP and UDP, where the fields in these traditional networking protocols, they are predictable in a guaranteed order and have guaranteed field widths. But in bundle protocol, it's quite the opposite. In version 6, you don't know how long your field is until you parse the entire field. Or in version 7, there's a lot of extra metadata that you would need some you would need more complex control logic to handle C-born encoding. And P4 has pretty limited control constructs for this. And also we ran into some hardware issues and also some issues with Intel's compiler that we are currently working with. But despite these limitations, we were able to come up with a proof of concept of a potential application, which is a bundle protocol translator, where in our setup, we have Ada and Rho. Ada is generating version 6 bundles and Rho is generating version 7 bundles. And usually these nodes wouldn't be able to talk to each other. But in our switch, we actually have the switch able to understand what is being sent into it and change the fields and convert it into the respective version of the bundle that it needs to be. And just as a side note, there are some limitations in this setup due to the complications I mentioned in the previous slide. And this could be useful for certain backwards compatibility situations, such as on the ISS that currently uses version 6 of bundle protocol. So we could toss that in there. But what I'm more excited about is the generalizability of something like this beyond translation, which is that we've shown that it is possible to get a switch to parse and understand bundle protocol fields. We can get a switch to modify these bundles at multiple layers. So not only the bundle layer, but we were able to get the UDP checksums to be properly updated when the bundles were changed to a different version and the IP checksums. We were also able to get this switch to send bundle telemetry to a controller. And then we were also able to get a controller that can modify this switch's behavior as needed. So based off this proof of concept, we came up with this architecture where it's a software-defined delay-tolerant network, where the nodes in your network could be just programmable switches, and you would put these programmable switches into clusters. And this clustering approach could tackle the issue of the issue of having reliable links between the controller and your nodes in your network. So in DTN, that's not going to be possible, but maybe if you have some smart clustering techniques, then you could have somewhat reliable links between your cluster controller and your bundle node. So for a more simple look at what this could look like, you can see cluster 2 and cluster 3, where each cluster, there's a controller, and you have the controller communicating with each of the nodes in your network. If you look at cluster 1, you can see a diagram of what one of these nodes looks like. You could use the P4 language and program a switch to get a switch to do everything that a bundle node needs to do to complete its store and forward techniques. Especially you could note that there's actually not just a communication link between this node and an external controller, but it's also possible to have an internal controller so that the node can self-regulate and manage all of its bundle node behavior. And then this is also useful in case the bundle node loses its link to the controller. The bundle node can still work on its own. But the controller can also take advantage of the fact that it's receiving information between all the nodes in its cluster and then make smarter decisions and then relay these smart decisions to the nodes within its network. Okay, and then, yeah, this would help, I think could help tackle the scalability issue of having large delay tolerant networks and managing these large networks by making it more manageable and feasible. So in conclusion, we proposed a software-defined delay-tolerant networking architecture as a way to manage large DTN networks, showcased a proof of concept of processing bundle protocol and hardware, and also detailed some of the challenges of working with the bundle protocol and coding schemes and hardware. Thank you, and I'm happy to answer any questions.
Thank you very much for the nice talk, Dominic. Yes, so again, for questions, I refer everyone to the chat window. We are still on track with time, so maybe we are going to have at the end of around 10 to 15 minutes available to have a brainstorming discussion if you want to stay online, so we can profit from that extra time if we keep the good track. So let's move to our next speaker. Our next speaker is Simon Rink. Simon is going to present us opportunistic and probabilistic forwarding in DTNs. Mentors are Juan Freire, myself, and Professor Holger Hermans from the Saarland University in Germany. So Simon, go ahead, the floor is yours.
So you can see my screen?
Yes, thanks.
Great. So then welcome everyone and welcome to my presentation about opportunistic and probabilistic forwarding in delayed tolerant network, which was my bachelor thesis project. So as you may know, there are a lot of routing problems we have to deal with in delayed tolerant networks. For example, uncertainty. So for example, satellites that were supposed to appear do not appear at all, or simply errors during the communications, or so-called opportunistic contacts. So while there are some cases where we can basically predict the future look of a network, so when satellites can communicate with each other, this might not be possible or only partially possible in some cases. So we might end up with communication opportunities of previously unknown satellites. So the question we have to answer here is how we can include them in our routing decisions in an optimal way. And of course, for each of those already exists some applicable solution. So for example, we have RUCOP that tries to mitigate the effect of uncertainties by trying to find the safest routes possible. And we have the OCGR algorithm, which is an extended version of the regular CGR algorithm that tries to, that also includes opportunistic context in its decisions. And the goal I had for my thesis was now to actually combine these two algorithms into one combined scheme, which is what I want to show you today. But before I will demonstrate that scheme, I will briefly show off the most important aspects of both algorithms. So let's start with opportunistic CGR, or short OCGR. So at its core, OCGR essentially works just as CGR in terms of the routing decisions. So we still work with some network where we have the satellites and the individual contacts. And the main addition is now that we also include so-called opportunistic contacts. That means contacts that were unknown before into our decisions. So in this example over here, we discover a new contact between nodes A and E. Since neither A nor E know anything about each other, this contact will set to last basically forever, which is of course unrealistic value. So in this example over here, it would end at 10 seconds. Which leads us then to the second core feature of OCGR, which is based on the fact that if satellites meet once, they will most likely meet again. So we now collect the appearances of said contacts in a so-called contact history, which is then used to predict the future outlook on appearances of that contact. We also assign so-called confidence X to that contact in order to give a estimation of how likely it is that it will really reappear. The actual computation behind the timings and the confidence itself is now not really important for the rest of the presentation, so I will leave that out for now. The only important aspect is that there is difference between predicted and actually discovered contacts. So great. So let's move now to the second algorithm I used, which is routing under uncertain contact plans, or short RUCOP. So here we use a slightly different model from what we have seen in OCTR. So we have here this failure probability assigned to each individual contact, which models the likelihood that a contact will not appear at all and thus offer no connectivity. Further, we have a timestamp assigned to each contact, which models the time interval during which a contact is active, but contrary to OCTR, those timestamps are not allowed to overlap and are thus distinct. And RUCOP itself is now more like an upper bound algorithmic idea, which is then actually implemented in LRUCOP, which has the goal of finding the safest routes possible in a network. And in order to do this, it actually computes all possible routes before any simulation is happening and puts them into a routing table, which is then sent to each node. So they can essentially just read up their current duration, so in this case, the time, and then infer the best action to be taken. Note that LRUCOP supports the transmission of multiple copies, so we can transmit multiple copies of the same bundle, where it is only important that at least one of them is actually received successfully, which offers a whole lot of new possible routes. So great. And these two algorithms I have presented just now have I now used to actually create a new scheme, which we called OL-RUCOP, so opportunistic LRUCOP. And the idea of OL-RUCOP is essentially that we take the uncertain network model as a base, so we still work with this model over here together with the routing tables and still want to find the best or safest routes possible. And the idea is now that we put the opportunistic features from OCTR on top of it. And I guess the problem with that approach is pretty clear. So we have these pre-computed routing tables over here, and here these newly found contacts. So there's actually no way that these contacts are already included in this pre-computed routing table. So the idea in order to solve this is that we actually develop a certain scheme which we use to update these routing tables at given points, so that these opportunistic contacts are actually included in our routing tables. And the question we have to answer now is how we can include them the best way. And here we decided that we actually have to solve two problems, mainly how we interact with the failure probabilities and also the timestamps in order to make them compatible with OCTR. And in terms of the failure probabilities, we have basically two cases, where the first case are discovered contacts, where we have chosen that those contacts always have failure probability of 0, which might seem strange at first glance, but remember that the failure probability essentially models the likelihood that a contact does not appear at all. But since a discovered contact has appeared by definition, we have chosen that it must have a failure probability of 0 in this case. The second case are the predicted contacts. So remember that they always have a confidence X that models the likelihood that this contact will appear. So we have chosen in this case that a failure probability, an according failure probability would be 1 minus X, so basically the opposite, so that the contact will not appear, which is of course just a first approach, and this can be refined in the future if more work is put into this topic. So this leaves out the second problem we had to solve, which was related to the time intervals. So remember that from the perspective of OCTR, we might end up with a situation like this over here. So we have these scheduled contacts over here, and then this discovered contact, which has this indefinitely long timer. And the problem here is now that this will essentially most likely overlap with the other contacts over here, which is a violation for RUCOP, or the model of RUCOP. And in order to solve this, we have actually chosen to split this discovered contact to as many subintervals as needed, such that they do not overlap with each other any longer. Of course, one might now argue that this actually breaks our model, since from the perspective of RUCOP, we have 3 contacts, while in reality, there's only 1. But remember that a discovered contact has a failure probability of 0. So 3 times a failure probability of 0 would be essentially the same as 1 contact with failure probability of 0. In terms of a predicted contact, we have followed a very similar approach, but I will not show that here now because of time restrictions. So this is then the very basic information or scheme we have developed during my bachelor thesis work. And of course, we also had to evaluate this new algorithm scheme, especially comparing it to the already existing schemes. And the results of that is what I want to show you now. So here you can see the delivery ratio, which is of course the most important aspect of our scheme since it tries to find the safest routes possible. And you can see here that we always compared the schemes with the native algorithm that is often used in TN routing, which is CGR. Also note that we also tested these three algorithms over here, but they are not relevant for this presentation due to time restrictions. But the happy news is that our new algorithm actually performed in our evaluations much better than the original LRUCOP algorithm and also better than the existing OCGR algorithm, but not much worse than Oracle versions of LRUCOP, where Oracle in this sense means that it is an upper bound algorithm which already knows all opportunistic contacts in beforehand, so it is not a realistic approach. But also in terms of other metrics, our schemes performed reasonably well. So in terms of the delivery delay, we also performed better than CGR, but of course worse than OCGR since the algorithm is not designed in such a way that it actually considers the delivery delay. And in terms of energy efficiency, OLRUCOP performed reasonably bad since we always considered 2 copies of a bundle. So the energy efficiency here relates to how many bundles were sent over the course of the simulation. So if we consider 2 bundles, 2 copies of a bundle, it always have to be higher, especially compared to CTR. So this then ends my presentation, and happy to answer any questions.
Thank you, Simon, for the nice talk. Yes, so again, move to the chat for the questions, and I will prepare to introduce Octavio Parsivaldi, who will, I think, Octavio, you were online, yes. So who will present the distributed database implementation for DTNs. Yes, I am also the mentor of Octavio. So yes, Octavio, the floor is yours.
Thank you, Juan. Oh, there's some echo, sorry.
Yes, I think there is some echo there.
Can you hear me now without echo?
Yeah, that's work. That's better.
I joined with the Mac because I don't have any cameras. Okay, so, well, I was going to present myself here, but Juan did it for me. I'm Octavio. I'm a student from Córdoba, from FAMAF. Oh, sorry. Give me 1 second. Okay, sorry about that. So today I'm going to be talking about my thesis. My thesis work is about the distributed database implementations for delay tolerant networks. This will be used for delay tolerant applications. I'm sure all of you are familiar with delay tolerant applications, but let's have an example here. Let's take this application, for example. We have an application working on the Earth, on Moon and Mars. And since there's a lot of delay between the Earth and Moon and Mars, we have to work with 3 separate instances of the application. For example, we will have one backend of the application on Earth, one on the Moon, and one on Mars. And to have that working, you will have to have 3 different databases working at the same time. So the problem with that is that if a user modifies one database, for example, modifies the database on the Moon, we won't have those changes on the Earth. So that problem should be fixed for any application that wants to be delay tolerant. So I have a like proposed a solution for this, and this is my package delay tolerant mongoose. So how to solve this with delay tolerant mongoose? So delay tolerant mongoose, it's a package that will replace mongoose. It's a wrapper for mongoose that has delay tolerant methods. It means that instead of updating your only database, it also forwards all the messages to all the instances you have of delay tolerant mongoose. And for doing that in a DTN, it uses a protocol called micro-DTN. So here is a graph explaining better how does delay tolerant mongoose works. Let's take, for example, you have a backend. Well, if for a normal application, you will only have those two squares, your backend saving data to the database and then reading from the database. But delay tolerant mongoose uses mongoose to save the information, but also it has a connection with micro-DTN in order to send all the updates to all the other instances. And well, it also receives that data for the other instances running on the DTN. So micro-DTN, as I mentioned before, is a protocol stack that has implementations of several protocols, such as the bundle protocol that is used on delay tolerant networks. It implements the bundle protocol version 6 and 7. They are the first protocol, I think, on implementing the version 7. And well, they have a lot of advantages, such as they have interoperability with other protocols, such as ION from NASA. And a nice thing about micro-DTN is that they have this thing called the AAP, the Application Agent Protocol. And it basically is like an API for applications to use micro-DTN in order to send messages over a DTN. So going back to the previous image, we have here that the literal mongoose connects to micro-DTN via a socket connection, and it uses that socket connection in order to send updates and receive updates from other databases. So here I have two short links in order if you want to know more about micro-DTN, because it's very interesting. And yeah, so well, I have the explanation for the AAP connection here. In order to use micro-DTN, first you have to register your application, and you will receive some ID. So in order to update other instances, you will have to have those IDs to send them messages. For example, I don't know, backend A and backend B, and you will send messages from backend A to backend B and from backend B to backend A. Okay, so this is basically what I said. It uses the AAP to synchronize data, and that's okay. So what is the difference between Mongoose and the delay-tolerant Mongoose? So Mongoose is a package for JavaScript backends to save data in Mongoose. But the delay-tolerant Mongoose adds some things on top of Mongoose besides the delay-tolerant functionalities. For example, it requires a configuration object in order to work. And well, it has obviously the new delay-tolerant networks. And, and another difference it has is the data usage of delay-tolerant Mongoose. It uses a lot more data because it needs to have like a file history for every file you save on the database. we will see more of that later. Okay, so the configuration it needs is these 4 things. The agent ID is the ID of your application. The list, the EID list is the list of IDs of your other instances of your application. Well, the host and the port of MikroTTN for the AAP in order to send and receive messages. So using the later and Mongoose is pretty simple. Once you install it in your project, let's say that you were using Mongoose for creating, for example, sorry, in Mongoose for creating a new object on your database, you will have to use the method create, or if you want to update one object in your database, you will have the update one method for example. But if you want to use the delay tolerant methods, you will only have to change the names from create to DT create, or from update 1 to DT update 1. And only with only that change, you will have the new delay tolerant functionalities, and you will have your distributed database up and running just by adding the configuration object and updating your methods from the regular ones to the delay tolerant ones. Here I have a list of all the delay tolerant methods. You don't have to read them. Just basically, you just have to change the first 2 letters for DT and then an uppercase. These are all the original methods from Mongoose. Okay, so we have been talking about distributed databases, but we haven't talked yet about the CAP theorem. So basically, this theorem states that if you have a distributed database, then you can have these 3 attributes at the same time: consistency, availability, and partition tolerance. Consistency is that you will always have the latest write on the database. And consistency sometimes is not compatible with availability, for example, because in availability, you will always have to make a response when a user wants to read the database. And you, in the later and Mongoose, you won't always have the latest write, because sometimes you don't know if you will receive something because of the big distances and the delay. So the lateral Mongoose can guarantee only availability and partition tolerance. Partition tolerance is that the system continues to function even if some messages are discarded. So the lateral Mongoose has these 2 attributes. I've been trying to work on making the lateral Mongoose a consistency system. For example, it will be useful for bank applications, because you will always want to have the latest write. For example, if you want to read about your bank account balance or something. So for those kind of applications, you will need a consistency instead of availability, for example. Okay, moving forward to the merge algorithms. When I say that the lateral Mongoose sends data to the other instances, sometimes that data is already being modified by that instance, and you need to merge the changes from one instance to another. So to have always the same information, the lateral Mongoose has 2 different algorithms. It has a local datetime. It's basically checking the latest write, so it discards the changes from one of the instances. And 3-way merge, that is the algorithm used by GitHub or Git. Sorry. So 3-way merge basically takes like 2 versions of a document and search for a common parent, and then it uses those 3 files in order to merge into one file. And this is probably the best way for merging files, but using three-way merge, as I will tell you later, it uses a lot of more memory than local datetime, that is basically using non-algorithm.
Octavio, sorry to interrupt. We are all a little bit over time, so if you could wrap up.
Okay.
Yeah, that would be great. Thanks.
Okay, so this is basically what I said before. And this is kind of the difference in kilobytes of usage of data between those two algorithms. This is having none, and this is using three-way merge. And okay, so about the future work of this, it should have, for example, more algorithms to merge and well have, like I said here, it should have a consistency. It should let you choose between availability and consistency, and that's some of the future work I will be doing into this thesis. So yeah, if you want to have a delayed run application and you already have a written one, you can use delayed run mongoose. And if you want to write a new application, you can still use it and have a distributed database system. So that's it. Thank you. If you have any question or something, you can write in the chat or write me an email or something. I will be happy to read from you.
All right. Thank you, Octavio, for the interesting presentation today. We are quickly moving forward to our next speaker. Olivier de Jonker will present today scalable, schedule-aware bundle routing. And Olivier is currently mentored by Marius Feldman. So yeah, Olivier, we listen to you.
Yes, do you hear me?
Yes, excellent.
So let me share my screen.
The volume is a little bit low. If you could somehow raise it, otherwise I think we can get it anyway.
Let me try to raise it. I'm
That's
sick,
better.
so
That's better.
Is it better? Okay. Up this and yes. Do you see a screen?
Yes. Perfect.
Okay. So let's dive in. So first, I will share my topics of interest, and then I will talk briefly about scalability in space networks, followed by the volume management, because it's the only independent feature I would present today that could be compatible with CGR, and then a brief preliminary evaluation of SPSN, including the contact partitioning, segmentation, feature. So as you can see, I mainly focus on algorithmic concerns of SABR, including pathfinding, so trying to solve an issue regarding the CGR, the extra routes that are not always the best existing routes in the sense of SABR. Then I also work on mutualization with shortest path tree. Of course, this comes with node multigraphs to have some kind of compatibility with multicast and shortest path tree support. I also care of the average computational effort. So this is mainly connections with the Yan's algorithm. I'm also interested in reutilizations of routes. That would be the routing tables in the SABR case, volume management with contact segmentation, and multicast and interregional routing. So first, some predictions. So we can expect an increasing number of contacts and nodes in the future, as well as an increasing size of the bundles with large science data and also a mean to reduce the layer overhead. And we can also expect an increasing number of interfaces with some dedicated relay nodes, and we might want to have simultaneous long and short range communications. So that also comes into play. So the expected challenges are volume management that will be stressed by extreme overlapping of consecutive contacts along the passes, as well as larger bundles. There will be also some computational pressure with scaling region size. We also have to address networking trade-offs, which are already in use today to reduce the computational pressure in CGR. So those three sub topics motivated the development of SPSN. And then there is also the interregional routing that can cause some concerns for the future. So I will only cover the volume management today because it's compatible with CGR. So the state of the art is that ACBR relies on the effective volume limit, which is a counter, like the volume of a contact that can be reduced after scheduling decisions. Then we have the earliest transmission opportunities, ETO, which calculates the ETO for the first top contacts depending on the transmission queues. We have also overbooking management for priorities, the scheduling, those kind of concerns, and queue delay, which is a recent features that extend ETO at the next hops after the first, but of course without queue access, and it relies on the volume that was booked on those intermediary contacts. So EVL can only be used for pre-filtering, because if there is some overlapping of the consecutive contacts, then we need to process a dry run to make sure that the bundle can get through. ETO can present some gaps with large bundles. So if a large bundle is being transmitted and during this bundle transmission, we trigger the scheduling of another bundle, then the ETO might be incorrect for this second bundle. And queue delay, which is a very great feature, can be also a bit inaccurate in case of extreme contact overlappings. So especially if the contact start time of the next contact is way earlier than the first one. Those kind of configurations. So we developed an alternative to deal with the volume management. So it relies on time segmentation of the contact duration. So in other words, we care of the bandwidth utilization intervals rather than the volume consumption. As a consequence, we don't require any more access to the transmission queues, which is I think an advantage to deploy those kind of technologies. And we rely on some storage about the segment utilization for rescheduling and volume booking cancellation. So how does it work? It's pretty simple. This is a scenario without priority support. So we have a contact between A and B, and at the initialization we have a single segment in green, and we will process some dry runs on the route to see if the route is suitable for this bundle. So that will be the CGR selection phase. If the route is selected, then we have to update the volumes, and So here we are. We can calculate where the bundle has to be booked. We can strip the segments for this contact, and well, now it looks a lot like EVL. But if we have another bundle that is sent later than the start time of a given segment, then the segment would be stripped at the right place, and we would create another segment before this first segment. So the segments which are in green are stored on the contact structure or object, and the segments in white are stored on a pair bundle basis to be able to be restored in case of rescheduling. And if we have a third bundle, well, quite trivial. It's pretty similar to what we did for the first bundle, but we do the same process from the second interval. So as I said, the contact segmentation can be deployed by attaching like volume manager to each contact. Can act a bit less like a black box, exposing some functions for selection, volume booking, and also rescheduling via cancellation. And so priority support is a very good candidate for the next version, of course, because priority, so it disappeared with BP7, but might be reintroduced in the future with extension block, for example. And of course, data rate variation are also good candidates to be supported by contact segmentation. So for the moment, for those two extensions, only proof of concept are available, but they already show very promising behavior, and they will soon be evaluated. So now we can switch to the preliminary evaluation. So contact segmentation was implemented for CGR in the IODTN SIM simulator to isolate the feature and see how it behaves. And we can see that we can have 1% gap. So better delivery rates or 2% increase. It seems pretty negligible, but two things in space environment, any level of improvement can be considered as a leap forward, and also those scenarios were not specifically designed to make contact segmentation shine. So the goal of this simulation was just to show that contact segmentation works as intended. We also provided some SPSN flavors, which is an alternative routing algorithm, which is very similar to CGR. And the backend pathfinding for those CGR flavors are the limiting contact approach with the first ending contact as a limiting contact leg. So that's not Jens algorithm. And the reason is Jens algorithm performs very badly in very large networks. You could see on the previous slides that we had scenarios with 200 nodes and thousands and thousands of contacts. We had to set a computational pressure limit for CGR ion yen to be able to have realistic simulation times So here we only compute maximum, I think 1,000 routes, 2 max per bundle, and still with those settings we reach scheduling process of 10-12 seconds. Which makes it hardly suitable for very large network. So the goal of this research is to show that there is some room for improvement in SABR, and we use SPSN as a mean to explore other paths. And for the moment, the result seems very promising. Some bibliography. And thank you very much for listening to me.
Thank you, Olivier, for the nice talk. So I ask people to post questions on the chat window, and we are moving to the end. So we have one last speaker today, Yael Kirkpatrick. The topic is cooperative clustering techniques applied to contact graph routing. And Yael is mentored by Rachel Dudukovic and Bob Short as well. So I leave the room to you, Yael, and I ask you, Olivier, to stop sharing so that Yael can take over and present the screen on her side. So thank you.
Thank you. Yeah, if you stop sharing, I'll just share my screen.
Yeah, the Zoom window disappeared.
All right. Let
Yes.
me see if I can somehow. Okay, it works. Okay.
It works. Okay. Okay, I see. Sorry for that.
Right, can you see my screen?
It's loading, I think. Yeah, it works.
Okay, great. Well, thank you. My name is Yael, and I'm going to be presenting some cooperative clustering techniques and how we can apply them to contact graph routing. And this is work I did over the summer at NASA Glenn with Rachel. So the challenge I want to talk about is routing in delay tolerant networks. So here we have to face many challenges that a lot of previous talks touched. These networks have frequent delays and disruptions. They have long propagation delays that we have to consider when scheduling communication between two nodes. And these networks have high node mobility, so a lot of changes can happen in a short time in the network. And currently the solution that DTN uses is contact graph routing. But the main issue with this routing with CGR is scalability, that CGR needs to know the entire network in order to just compute a single route to route through the network. And in very large networks, this can become extremely slow. So the solution I'm going to be talking about for a little bit is clustering. So I'll explore some various clustering algorithms and techniques, and I'll see how we can adapt them to the setting of CGR and propose a protocol, a delay tolerant clustering protocol that we can use in DTN. So a little bit about CGR. I'm sure everyone here knows what CGR is, but just to recap, in CGR, we represent these networks as a multigraph or a graph, where a contact is a period when two nodes can communicate, and this is computed on Earth and distributed in the network as a contact plan. And contacts are represented as edges in the graph, where the connectivity or the existence of these contacts is can be represented as data along the edges. So this 2,5 would mean that an edge exists at this edge, or this contact exists at times 2 and 5. And now our problem of routing through the network turns into pathfinding on the graph. And our goal is to find the fastest way to send data through the network. But the problem is that we need to know the entire network in order to compute this path. We need to know if by the time we reach a certain edge, like if the time that we reach it will be relevant, will this contact still exist, or will it be in the future? Will we have to wait? So currently with these techniques, in really large networks, it can take a very long time to compute paths. And So a solution I propose is clustering. So in this approach, we divide the network into subnetworks or clusters. And now every node doesn't really need to think about what happens inside of other clusters. So say we're a node in this cluster A, then we don't need to think about the fact that cluster E has satellites and how they communicate with each other or whether or not they can see each other. We just need to know that there's this abstract cluster E out there. So this reduces computational overhead because it just makes a smaller graph that every node needs to think about. But beyond that, it also allows us to integrate commercial networks by just considering them other clusters in the network, or it allows to combine different kinds of networking like cognitive networking and software-defined networking. So now the challenge turns into how can we divide the graph or the network into clusters? Because if we need to know everything about the entire network in order to decide how to divide up our clusters, we have the same problems we had before with routing. So the challenge is to create a clustering algorithm that uses local information and low communication overhead in order to divide the network into clusters. So here I can introduce the idea of game theory. So this is a branch in mathematics that studies conflict and cooperation between intelligent, rational decision makers. So as a definition by example, we can think of a game of sharing resources, where players can either play fair or they can be greedy. So if a player is greedy, they play as a hawk, and if they're sharing, they're playing as a dove. If two doves decide they want the same resource, then they just split it 50-50. If a hawk and a dove want the same resource, the hawk just takes it to himself. But if two hawks want to share the same resource, then they fight over it and they both end up losing. So if everyone in this game decides to play as dove, someone could just be a hawk and come and take everything from them. But if everyone's playing as hawks, then no one gets anything because they're just constantly fighting over resources. So these individual strategies feed into some global equilibrium where some players are hawks and some players are doves, and it doesn't make sense to change your strategy because you're not going to gain anything more on average. Another example of a game is a cooperative game where instead of players trying to play against each other and optimize their own success, they try to optimize something together. So an example for this is a coalition game where different coalitions are awarded different values and the players need to decide how to divide this value between them. So as an example, in this green box, we have different prices of 3 fruit smoothies. So we can see that the smoothie, they're worth different amounts. So we shouldn't just distribute the money evenly between the fruit because some of them are worth more than others. For example, all the ones that have pineapple cost more than the others. So we need to find a way to distribute this resource between them in a way that is fair. And the solution to this problem is a notion called a shapely value, where we give each participant some value that depends on their contribution to the entire coalition. So now we can apply these ideas from game theory to this problem of clustering. The first way we can apply it is using this idea from cooperative game theory. We can create clusters around the most central nodes. So we'll select the most central nodes as cluster heads, and then each node will just join its closest cluster head, and that will be its cluster. And in order to measure centrality, we can give some notion of value to clusters and measure the shapely value of nodes, and then use the ones with the highest shapely value to become the cluster heads. Another way we can use game theory for clustering in networks is using a non-cooperative approach, where we're thinking about how to choose cluster heads. Because again, this is something that you don't necessarily want to do because it wastes some energy. So we create a game where players want to optimize their residual energy. And a dove strategy in this game would be to volunteer to be cluster heads and run the network. And a hawk strategy would be not to volunteer. So it doesn't make sense for everyone to be doves because we don't really need everyone to be cluster heads. That's just wasteful. But also, if no one volunteers, then we lose because we need someone to do that. So this leads us from these individual strategies. We find some equilibrium state where some players are cluster heads and some aren't, and it doesn't make sense for them to change their strategy. Another approach we can use for clustering just uses some graph theory. So we can use a local dynamic clustering approach where we optimize some measure of fitness for a cluster. So we don't really need to worry about the exact equation here for a cluster fitness. Just notice that it only uses 3 parameters regarding a cluster. It uses the cluster size, the internal degree of the cluster, and the external degree of the cluster. So since these are only 3 parameters, they're all just integer parameters, they're very easy to maintain. So if a node joins the network and it wants to decide which cluster to join, it just needs to query other clusters, gets these 3 integer bits of integer parameters of information from each cluster, and then it can calculate pretty simply and see which one it would make sense to join. So now we can combine all 3 of these approaches to make a delay tolerant clustering protocol. So when we initialize the clusters, while we're computing this, we can do it back on Earth when we're computing these contact plans, and we have all this global information of the network. And then we can use our cooperative game theory approach to find the best cluster heads and the best clusters to divide up the network. We can also use this cooperative approach that needs this global information when we're splitting clusters. So if a cluster becomes too big and we want to split it up into smaller clusters, we can use this same approach. But during regular maintenance of the network, while when a different node joins or nodes move around, we can just use this dynamic local approach, which only uses the few parameters about the clusters to have nodes move around clusters and join different ones. And finally, if a cluster head decides or leaves the network, dies, decides it doesn't want to do this role anymore, or two clusters merge and we need to find a new cluster head, then we can use our non-cooperative game in order to select a new cluster head while trying to optimize residual energy of nodes. And using all these together, we can call this delay tolerant clustering protocol. So to recap, CGR requires distribution of contact plans through a very large network, and updating this on all the nodes becomes very, very slow. So defining a network regions and dividing a network up into clusters, it can give us a lot of benefits in runtime and scalability. And it can also account for different paradigms, deterministic and opportunistic paradigms. And it can give us other benefits like developing association for trusted neighbors, other nodes that tend to be in the same cluster as you and you know them very well. It can also allow interoperability between different kinds of protocols. We can combine different kinds of networks in our space internet. And finally, it can also develop a hierarchy among nodes. So we could have some nodes that are potential cluster heads and might need some more robust hardware and some more capable computational systems. And some nodes can just be some low-cost little nodes, and they just don't be cluster heads, and they just rely on other nodes to manage the network around them. And using this approach and incorporating an HGTN could have effect on all these different projects that NASA is involved with right now. It could potentially be used in the International Space Station DTN network. It could potentially be used in future LunaNet missions, and it could be used in the laser communication relay demonstration. So yeah, I'd like to thank my mentors from this project over the summer, Rachel Dudukovic and Bob Short, and all the interns that I got to work with. And while we're here, I wanted to mention that GRC is hosting a workshop on cognitive communication this June. And if anyone's interested, there's more updates on the website. And yeah, I'd love to take questions if we have time.
Excellent, Yael. Thank you very much for the very interesting talk. Yes, I left a question on the chat window.
Okay, I'll look at that.
Meanwhile, we have 8 minutes left. So maybe I want to open the microphone for everyone here, every student, every participant of this session, to maybe bring up any possible topic or thought about the talks that we have today or the rest of the workshop. So yes, kind of a free session style now. So yes, if anyone has any comment or question, feel free to unmute and comment. Or maybe also comments from the supervisors. I see that Robert is connected, Rachel as well. So if there is also any comments from the supervisors, it's also available.
It's interesting to see there's a lot of kind of common, it seemed like there's commonality between all the presentations that the students were working on, like the more advanced routing techniques and moving towards opportunistic routing. So it was very interesting. I enjoyed seeing what everyone was working on.
Right, I fully agree. So I think I personally, I feel this session was really interesting because it's a very good way for students to synchronize also among themselves on the different topics. I'm happy to see that there is no significant overlap, which is a good news, I think, which kind of speaks about the, the different axes and the different areas that actually Space DTN offers to work on. So also, I think this session was really, really interesting to me as well. Right. So any other further topic or comments? Otherwise, I think we can start to think on closing the session today.
Yeah, I'll throw a comment out there. I noticed in the chat that Timothy and Simon have been talking about Simon's opportunistic CGR, which was also really interesting to me. One of the ideas that has been kicking around over here is the idea of generating a contact plan sort of dynamically, right? The idea, like Simon, you were talking about, if I see a satellite at one point, I'm likely to see it again. And so you can sort of make some predictions about what your future contact plan could look like. I'm curious if that's something that anyone else has given some thought to.
Simon, you want to take that one, or?
I'm not really sure if I understood the question correctly here. So the idea behind OCTR, so it was not developed by me, of course, but the idea behind OCTR is essentially that based on history, we have collected where all the contacts between a given node pair has appeared. We basically want to make this prediction. So the more regularly this contact appears, the higher the confidence in the end will become. So it develops kind of over time. And what is also important in this aspect, what I did not mention in the presentation is, but these contact histories and therefore the predictions will not only be made available to these two node pairs, but when contacts meet, be it in a discovered or in a regular scattered way, they will in the end exchange these individual contact histories and update them accordingly, such that after a given time, this knowledge will be covered in the whole network in the best case. So we might end up with a kind of scheduled contact plan at the end where we have a lot of predictions and therefore many ways we can actually route our bundles.
Yeah, okay, interesting. Yeah, I guess what I've been, so one of the things that I've been thinking about is that we have a bunch of commercial service providers who are building their own networks. Think like Starlink, think Iridium, stuff like this, who might know who might understand their networks reasonably well, but won't know about other networks until they get up there, right? This feels like a good opportunity for OCGR to be effective. But obviously the thing is that there's a lot more detail in there, and how do you get the different companies to actually be able to talk to each other? But yeah, so yeah, just some thoughts that I had kicking around. Thanks for sharing.
Sure. So on that same line, so what I feel is that I think you are identifying a gap that is not fully covered yet. So because OCGR kind of mimics a little bit how Prophet works, in the sense that if I see one node at this moment, and then I see that node again tomorrow, and I start to feel kind of a frequency of encounter, then I kind of increase the probability that I will meet that node in the future. But it's just a purely encounter-based estimation. There is no orbital dynamics involved in this probability or this frequency estimation, basically. So I think there is room actually to somehow step in the middle between OCGR and what I can say, CGR maybe, where the probability of meeting someone again can be somehow enriched by some orbital dynamics parameters that can be exchanged during the contact, for instance. I think that is a gap that I have not seen covered by any solution yet.
Yeah, it would be interesting to see like a low swap orbital analysis package or something that would allow you to say transmit TLE data as part of your discovery protocol and then run the computation locally. But that seems like it would be difficult.
So sounds interesting because that would basically allow different operators to self-discover each other, right? Without like a centralized administration to do that for them.
Yep, decentralization is something I'm very interested in for sure.
All right, so thank you guys for the comments. And with this, we are right on time to close the session today. I want to thank everyone for joining, especially students, to presenting their very interesting work. And yeah, so as I mentioned before, this is recorded and will be made available to all of you as a future material to use and study. So thank you everyone for joining, and I wish you a very good day wherever you are.
Thank you. Have a good day.
Thank you all.